Now that we learned about the necessity of some measures to measure variability in data, let's learn about variability measures, starting with the range. What is the range? The range is the simplest measure of variability in dataset that you can use. And it's actually very easy and simple to understand. The range is just the difference between the largest value in your data and the smallest value in your data. So it's going to be um, the largest value minus the smallest value. The problem with range is that it actually ignores the distribution in your data and only focuses on the range of your data. It's going to be only on the minimum and maximum in your data. So you don't really know about the distribution between these two values, the minimum and the maximum, the smallest or the largest. And also another problem with the range is that it is sensitive to outliers. And it makes sense because outliers are going to be extreme values that are either the smallest value or are the largest value. So if you actually add outliers into your data, then it's going to certainly change the range in your data. Measures of variability, the idea of deviation from the mean. What other methods can we actually use besides the range to measure variability or dispersion in our data? How about this? We actually find the deviation of each data point in our data set from the mean, and we can come up with a measure based on that idea. Let's try this. Suppose we have, this is the graph of our data, and these are our data points. Suppose this is the mean, the average of our data. So what we're gonna do is we are going to find the deviation or the distance from each data point from the mean. And then, for example, we find the average deviation from the mean. Average deviation. It sounds like a good idea, right? All right, let's try that. Let me actually get rid of these lines first. Let's do it and apply an example. Suppose we have this set of data, 8, 4, 9, 11, and 3. The average of this data is 7, and the range is 8. So what we're going to do is we're going to find the deviation of each data point from the average. For example, the deviation of the first data point 8 from the average is 8 minus 7, which is 1. So 8 is 1 deviation away from the mean. For the second data point 4, the deviation is negative 3. For 9 is 2. For 11 is 4. For 3 is negative 4. So let's find the average. If we sum these values up and then find the average, actually it becomes 0. And that's problematic, right? The average deviation can become 0 because of what is called as cancellation effect. Cancellation effect. So we need to do something about this problem, the cancellation effect. We need to do something to avoid the cancellation effect. Try to think about a solution for this problem while I'm trying to erase these lines. What can we do about this cancellation effect? What did you think about a solution? What was your solution? Let's move forward with a solution. A solution to the problem that we have with finding the deviation from the mean, the average deviation, that we had the cancellation effect. A solution to that, it leads to a method called the standard deviation. Let's see how it works. Let's go back to our previous example that we have. So we wanted to find the deviation and the average deviation from this problem for this set of data. So the problem that we had was we had positive and negative deviation. So we would end up having zero summation and also an average of zero. This is called the cancellation effect, because we have positive values and negative values, and these two sets, positive and negative, would cancel each other out. So the average deviation would be zero here, but that doesn't mean that the deviation is zero. We have deviation here. Some of them are positive, some of them are negative. So what should we do about this? One way to do this, to tackle this problem, is to actually square each deviation. So for example, instead of just 1, we square the deviation, that would be 1. So the deviation, for example, is -3 here. We square it, and the square would be 9. The deviation here is 2. We square it, and that would be 4. The deviation here is 4. We square it, and we get 16. The deviation is -4 here, and we square it and becomes 16. So as you see here, what happens is we get rid of negative values. We would only have positive values. And if we sum them up, we would have a non-zero value because there is no cancellation effect. We would have a positive summation. So now we can find the average, but there is a catch here. Because we squared each deviation, we need to take this squared effect out of this equation, so we would have a fair average. One way to do that is actually to get the square root of the average of this. So what we would do is we get the square root of the summation here that we have, the summation of xi minus its average squared, right? Average squared, and then divided by the number that we have, okay? So that's one way to do that. So let's actually look to this in real application. Let me get rid of these lines first. When we want to apply this in real life, actually, there are two way to do this for two different set of data. If we are working with a sample data, suppose that we are working with sample data. Let's see what would be the formula for a standard deviation for a sample data. Suppose we have a sample data with n items in it. So our data has n items in it. The standard deviation for a sample is shown by a small s, because s stands for sample standard deviation. Okay, so we show it by s, and it's equal to this formula. So it's equal to the square root of the summation of a squared of the deviation from the mean. This right here is x bar. As you know, x bar is the mean of the sample, mean of sample. And then we divide it by n minus 1, and we get the square root of all of that value. Why do we divide it by n minus 1 and not n? It's actually an advanced question to ask that we are not going to cover it in OMS 40. We're going to talk about it later in OMS 41. So right now, just bear with this and remember that for this standard deviation of sample, we divide it by n minus 1 and not n. Okay, so that's the formula for a standard deviation for the sample. It's noteworthy to say that we show the standard deviation by s, and a square of this s squared, is called variance. So variance is just, this is r. Variance is just a squared of a standard deviation, okay? So the standard deviation is shown by s, and the square of that value is defined or told or named as variance. Let's see how this works for population. Let me get rid of these writings first. For the population, suppose we have a population of size n, capital N. Okay? This is the size of this population. The formula for the population standard deviation is as follows. First of all, we show it by sigma. This is called sigma. It's a Greek letter and it's called sigma. And it's actually similar to what we had before for the standard deviation of sample, except that we use the mu here. This is called mu, and it's shown by this Greek letter mu. Mu. So the average of the population is mu. We use mu to represent the average of the population, and then we divide that values, the summation, by capital N. All right. So this is the formula for the standard deviation of population. Make sure to notice this. Sigma stands for standard deviation of population. S stands for standard deviation of sample. So this is for population, that was sample. X bar is the average or the mean of sample. Mu is the average or the mean of population. For the standard sample, the standard deviation, we divide the value by n minus 1. For population, we do divide it by n. So remember all this. Also, the population standard deviation, sigma, if you square it, this becomes the variance of the population. So sigma squared is the variance of the population. All right. Let's summarize what we have learned here in a nice table. So we want to talk about these population parameters versus sample statistics. So for population, we have parameters, average, for example, a standard deviation, variance, and for sample, we call them statistics, if you remember from the previous lectures. So let's show them in this nice table here. So in the first column, we have the measures here. These are the measures. We have the mean, the variance, and the standard deviation. For the population, we call these measures parameters. For example, we show the mean of population by, if you remember, by mu. This is called mu. Mu. And for the sample, we show it by x bar. For the variance of the population, we show it by sigma square. For the sample, it's s square. The standard deviation is just the square root of the variance. So for population, it's sigma, and for sample is just s. So this table is going to help you to just summarize all these, what we have learned so far. Sample standard deviation that we shows it by small s. Let's take a look at an example here. We have this set of data, 10, 12, 14, 15, 17, 18, 18, and 24. We have actually 8 number of data here, right? The average is 16. So we need to pay attention that it says sample of data. So we are working with the sample. That's why we show the mean by x bar. If it had told us that it was population, we would have showed it by sigma, right? But this is a sample, so we show it by x bar. All right, so we want to find a standard deviation for this set of data, which is a sample. Remember how to do that? So let's find it. The formula was S, the standard deviation of the sample, S is equal to the square root of the summation of deviation of each data point minus the average squared divided by n minus 1, right? This is the formula, remember? All right, so let's do this for this formula. Let me get rid of this first. Okay, if we plug in all the numbers in the formula, this is what we are going to get. And this will be S, the standard deviation of the sample, which is actually a measure of the average scatterness around the mean, right? Because it's average. It's the average of dispersion or scatterness of all these data points from the average in your data, 16, right? So the standard deviation of this data set is 4.31, almost approximately. Right, now that we learned about measures of variability, in addition to the central tendency measure that we learned, let's apply it to our previous example that we have, the average age of classes. Remember, we had two classes, right? So this is the plot of the ages of two classes. Class 1 shown by plot in color green, and the class 2 is shown by blue color. These are the central tendency measures for these data, which weren't that much helpful. We couldn't really get a sense or understanding about the variability of the, especially in second class, the ages of students in second class, which is much wider than the first class, using the central tendency measures such as the mean, the median, and the mode. Let's compute the variability measures that we learned, the standard deviation, the range. So class 1, this is the age of students for class 1, and this is the age of students for class 2. The range for the first class, the age of a student, is the maximum, or the older students, which is 32, minus the youngest student, which is 27. So the range would be 32 maximum, the largest value, minus the minimum, the smallest value, 27. The range is 5. The standard deviation, if we run the formula, is 1.79. If you do this for this second class, the range is the maximum minus the minimum. The oldest student, or the maximum value here, is 41. The minimum value is 21, or the youngest student. So the range is 20 for the second class. If you compute the standard deviation using the given formula, is 7.54. So now if you actually compare these two new measures of variability that we computed for these two classes, it actually gives us more information, because 20, the range for the second class, is much larger than 5, the range for the first class, and also 7.54, the standard deviation for the second class, is much larger than 1.79, the standard deviation for the first class. So this gives us a deeper understanding into the data, besides the central tendency measure. It gives us actually the variability understanding in our data. So let's actually put this table in. We added the two new measures, the range and a standard deviation, in addition to the mean, the median, and the mode, which are central tendency measures. So now, given these two measures, we can say that, okay, it looks like central tendency measures, we see that there's not much help in understanding the variability. It looks like the central tendency are almost equal, or we cannot go further than this, that the average is exactly equal, or we cannot but figure out the variability of the age of the students in two classes. But looking at the variability measures, such as the range and the standard deviation, we see that clearly the variability in second class is much larger than the first class. All right. All right, let's work on a practice problem for the materials, the new materials that we have learned. We want to find the variance of the following population data. You need to pay attention to these key terms, variance and population, to make sure that you use the right formula. All right, so we have this set of data. Please find the variance, pause, work on the data, and find the variance, and then come back to see the solution. All right, so let's work on the problem. We show the variance for population by sigma squared, and the formula for that is the summation of the deviation from the mean, which we show it by mu for the population. So the deviation of xi, each of your values in your data set, from the mu, the average of the population, divided by n, the size of the population. So n here is 1, 2, 3, 4, 5, 6, 7, 8. So n here is 8. And mu here, the average is 5.14. 5.14, only two decimals. If you compute this, sigma, the variance sigma squared would become 6.408, three decimals, if you want to go with three decimals. All right, let me get rid of this and then we work on another example. Calculate the standard deviation of the following sample data. So this time you need to use the formula for a sample and for a standard deviation. Make sure that you always pay attention to these key terms, whether it is a sample data or a population, and whether it's asking for a standard deviation or for a variance. So please go work on this. Pause on the video. These are the data set. Pause on the video and then come back to see the solution. All right, let's work on the problem. So we are looking for a standard deviation of sample. We show it by S, a small s, that's the standard deviation for sample. And the formula is the square root of the summation of deviation of each data point from the average of the sample that we show it by x bar. This is a squared, then divided by n minus 1. What is n here? We have 1, 2, 3, 4, 5. So n here is 5. And the average, if you compute it, the average of the sample is 17. If you compute the standard deviation is actually equal to 7.176. 7.176. This is the three decimals, the standard deviation of this sample. All right. Let's work on another practice problem. Please use statistics that you have learned so far to compare the following set of sample data. So you have three set of sample data, set A, set B, and set C. Use the statistic that you have learned to compare these. So first of all, this is a sample data that's going to help you to know which formula to use when you want to find the standard deviation. Okay, so what you need to use is you have to compute the mean, which is x bar for sample, right? The median, the mode. These are the central tendency measures. And also you have to compute the range and a standard deviation S and S squared, and compare this set of data. So for the three sets, set A, set B, and set C, compute these statistics. This is the first one, the second one, the third one, the fourth one, the fifth one, and the sixth one. So you have to compute 6 statistics for each of these data sets. Please pause and then come back to see the solution. All right. So let's solve this problem. We have three set of sample data we want to sample data, we want to compute statistics for these, such as mean, median, range, and a standard deviation. I'm not going to show you the variance because it's similar to the standard deviation. It's just in standard deviation squared. So if we compute these statistics for the first set, it's the mean is 17, the median is 16, the range is 18, the standard deviation is 7.18. For the second set, the average is 20, the median is 20, the range is 6, and the standard deviation is 2.5. For the third set of data, the mean or the average is 27, the median is 29, the range is 33, the standard deviation is 13.2. So now you have a combination of central tendency measures and variability measures to compare these three set of data. That's going to give you a more understanding, a deeper understanding of these three sets of data. I'm going to go a step even further, and I'm going to actually plot this data as you see here. So the set data C, as you see here, it has a standard deviation of 13.2, which is much larger than the standard deviation for set B and set A. So it's more widespread. The average of this data set is also higher compared to the set B and set A. And also it has higher range, right? So set B, on the other hand, which is shown by the orange color here, is the least various or has the least variability among these three sets of data. So this is how you would use these statistics or these parameters if we were talking about a population to compare different sets of data.